Alright, physics. We left off with like electric field. We had talked about static electricity and what happens there. I gave you, you have your little bit about the charge of the proton and electron. Here's the next thing, right? Because we're done with basically static charges, with static electricity and electric fields of objects that aren't moving. We have to get into the electricity that powers your phones, powers your laptops, tablets, like speakers, even your computer, stuff that plugs into the wall, TVs too, to some extent. Because the kind of electricity, and I brought up the electricity reference table page here because I'm going to need it in a little bit. But the kind of electricity we need to focus on, and our next, like, big topic here, is circuit electricity, right? Making a circuit and creating something that runs off of electricity. Now, in order to make a circuit, I need, like, very specific things. In fact, I actually need 3 very specific things. The first object that I need to create a circuit is basically your source of electricity, right? Source of electricity. Specifically, you need a voltage source, which typically is a battery. So I need a voltage source. I also need something for charge to move through. Right, so the voltage source, the battery, gives charges a bunch of extra energy. I'll explain what voltage is soon, but voltage source gives charges a bunch of extra energy. It pushes those charges along, so they need to move through something, right? Some kind of conducting material, most typically a wire. And the last thing is, it's really dangerous to just give charges energy and send them on their way. You want to give them energy, send them on their way, and then force them to use that energy in something. So the last thing you need is something to use the excess energy. Something to use the excess voltage, right? And generally speaking, we call these things resistors, because they will resist the flow. They will try to slow the charges down, so charges have to expend energy in order to use them, right? Now, there's a term here, voltage, that we need to, like, kind of define, right? Voltage is the work done on a charge, or I'm going to say the extra energy, because I don't want to say the energy as if, like, charges don't have a, like, baseline amount of energy. Charges have a certain amount of energy to start with, and what the voltage source, what the battery does, it gives it excess energy. So the excess energy per charge, right? And what that means is that voltage is a capital V. It equals W, which you should remember before. Capital W is work per unit charge. And it's measured in volts. Now, if I zoom in on our lovely reference table page, you should notice, look, there it is. Voltage is work. How much work do you do per charge, or how much energy does each charge have, right? 1 volt is 1 volt is 1 joule per Coulomb. So J over C, and it's measured in volts. Right? The next piece, we have, the charges have to move through a wire, right? As charges move through a wire, as they pass through, they have a certain speed at which they move. That speed, the rate of flow of charges as things go by you, is the current, right? So each circuit has a speed, and they have a speed limit, but they have a speed at which charges move, and that's the current. So current is how many charges pass in a second. Right? So current is represented by the letter I. It represents how many charges go by per unit second. We measure this in amps. The amperage, or the amps, that are in a circuit is how many charges go by. 1 amp is 1 charge per second. So if there's 1 charge that goes by every second, that's 1 amp. If we doubled it, it'd be 2 amps, and so on, and so on, and so on. Right? Now resistors have a property that we call, shockingly, resistance. Resistance is the difficulty for charge to pass through a material. I'm gonna put that word down here. Right? And how this works out, what resistance ends up being. Resistance is voltage divided by current. Right. This equation will not often be displayed by that, even though it's on the reference table like that. Like, you can see it just down there. I've just rewritten those 3 equations, right? V equals W over Q, I equals delta Q over T, and I said this. However, more commonly, you will see that V equals I times R, and we'll talk about that. Now resistance, I should say volts is a capital V, amps is a capital A. This is measured in ohms. Ohm, like you're meditating, ohm, but ohms. And the symbol for this is that horseshoe. It's a capital letter omega. It's a Greek letter, right? This equation is sometimes referred to as Ohm's law, right? So, ohms. Now, these 3 equations, 1, 2, 3, technically 4, right? I'm sort of counting this as a separate equation, but these equations constitute the basics of circuit electricity and how things are related, right? Batteries on their own, typically like a AA, AAA, C or D battery, even the watch battery or like the key fob battery in your car, they provide 1.5 volts of electricity, or 1.5 volts of voltage, which means they give each charge 1.5 joules extra energy, right? So it's not a ton of energy, but depending on the circuit, they may move very quickly through the wire or slowly because of the amount of charge, right? Something to keep in mind here with Ohm's law is that voltage and current are directly related. Voltage and resistance are directly related. Current and resistance are inversely related. That should kind of make sense. Think of resistance as how difficult is it to move. Think of current is how fast can you go. If resistance is really high, the current is going to be low because it'll be difficult to move through. If the resistance is low, the current will be high because it'll be easy to move through. All right? All right, so here, this is just basics of circuit electricity. What I'm going to do is I'm going to throw an assignment on my CBA. It's going to be questions, again, Green Book or Regents, right? So I'm pulling a lot from the June 2015 Regents. It happens to be the first Regents available in the little Green Book. So June 2015 Regents, it's going to be a few questions about electricity. I think somewhere between 5 and 10 questions on those equations, like using these equations, getting used to reading, kind of looking at them. I want you guys to kind of work your way through them and try to figure out, like, right, work, charge, time, all of this stuff. Work out reading these equations, interpreting what's happening, right? On the reference table page, we are slowly but surely making our way through electricity. So we've talked about this law, which is Coulomb's law. We've talked about this, the electric field, that was in the last video. And now we've talked about these three equations here, right? The next one that I'm going to address is actually the next two that I'm going to address are these two. I'm intentionally going to skip this resistance equation. I'm doing it intentionally. I'm not trying to do it to be difficult, but this is one of a handful of times that I'm going to kind of change the order here. I'm going to talk about this last because it's very specific, and it only comes up in a very particular context, whereas these equations can be kind of almost anything else. These could be like asked in many different ways. This can only be asked in one way. All right. So again, check my CBA. You'll see the assignment there. Make sure to turn that in before your B-Day. I don't know. But turn them before A-Day. I don't know. I don't even know what letter date today. I'll put the date will be on the assignment. Let's just put it that way, all right? If you have questions, if you want to ask about electricity, if you want, bring it into class, send me an email. I really actually like talking about it in class because it lets us, make a discussion out of it. And I don't mind doing, like, the boring notes and stuff here. So bring questions into class. We'll talk about it. Otherwise, until next time, whether that's class or the next video, I will see you. Take care, kids.